Good afternoon and welcome everyone for the second webinar of this year by the Institute of Engineers Sri Lanka WA chapter. So today's, I am really great to introduce our speaker, Nimila, and he's giving the presentation on rare earth permanent magnets and green dreams, Sri Lanka's rare earth odyssey for harnessing the hidden treasure. Thank you, Nimila, for accepting our invitation. Thank you very much, and we welcome you for our webinar series today. And before we start the presentation, I will give you some sort of housekeeping rules. Yeah. So once I finish this introduction, I will pass on to our coordinator, Ravindra. So he will give you a little introduction about the speaker and the title today. And then before that, after that, we have 45 minutes for the presentation. Basically, Nimila can do his presentation. Then after that, we will come to the Q&A session. Even during the presentation, if you have any questions, you can raise your hands or you can put your questions onto the chat box. And if it is, we think that it's not disturbing the flow of the presentation, we can take it during the presentation, or otherwise you can wait until the Q&A session comes after the presentation. So during the presentation, we kindly ask you to mute yourself, your microphones, so that we are undisturbed throughout the presentation, right? So I think you can understand the situation. So, and also, maybe some of you are interested to getting CPD certificates from this presentation. So if you are interested to get, please send us an email to the secretary@ieslwa.org email account, or otherwise you can just type to the chat box. Then we can arrange to send you a CPD certificate for the participation of this webinar. I think that's it from my end. And also a big thank you to Ravindra Sagadu for coordinating this webinar. And he will give you an introduction to the title and the presenter today. Over to you, Ravindra.
Yeah, thank you, Taranga. And yeah, today I'm going to introduce a young Sri Lankan scientist, I would say, engineer Nimila Dushanta, to deliver this lecture. And without taking much time of his valuable lecture time, I will quickly introduce him with his credentials. Yeah, Nimila is a mining engineer who graduated from Faculty of Engineering, University of Moratuwa, specialized in mining and mineral processing in 2015. And then he completed his MPhil at the same department in 2019. And he stepped on to PhD in 2019 at the same department in mineral processing, focusing on development of extraction techniques for rare earth elements from diverse geological sources. And he had many PhD publications, and one of his PhD publication was selected as a leading article of the week by Global Rare Earth Industry Association in Belgium and included it in their weekly newsletter. In 2020, Nimila expedited his, led onto an invitation from a lecture on rare earth elements and uranium processing at University of Science and Technology Beijing in China. 2021, he was invited once again to deliver a keynote speech on rare earth elements magnets and their future challenges at the 9th International Conference of Metallurgy, Technology and Materials in Zhengzhou, China. The same year, he was awarded the PG Curie Medal as a Young Geoscientist of the Year 2021 by Geological Society of Sri Lanka, recognizing his outstanding contribution. 2023, once again, he participated as a speaker in webinar on rare earth elements, supply chain diversification, organized by Minerals and Mineral Materials Journal. Engineer Nimila actively engages in collaborative research with Monash University, Malaysia, and is the REIA in Belgium, Ceylon Waste Management Private Limited, and Lanka Phosphate Limited at Pavala. Currently, he serves as a lecturer at Department of Applied Earth Sciences, Faculty of Science, Uwelasa University. So if I keep on reading, a lot of credentials registered from his career, but I make it shorter. And now I will pass it to Engineer Nimila Dushanta to deliver his speech. Over to you, Nimila.
Okay, thank you, Engineer Ravindra Salgado, and thank you for the invitation as well. And it would be a great honor that I can address this forum and sharing my all research experience and publications and things related to these rare earth elements. And first, I would say that hello to everyone. Today we are diving into the worlds of rare earth permanent magnets and how they are helping us to achieve our green dreams. So I'm going to explore how Sri Lanka's hidden treasures can play a big role in this journey. So again, welcome you all to Rare Earth Permanent Magnets and Green Dreams, and then Sri Lanka's Rare Earth Odyssey for harnessing the hidden pressure. So now let's move to my content of this presentation. I will start by looking at the current status of the rare earth industry and then explore how rare earth permanent magnets contribute to achieve our climate targets. After that, I will focus on Sri Lankan's journey in rare earth elements with two case studies, Paula phosphate deposit and gem mining waste. And finally, I will wrap up with some conclusions, discuss challenges we face, and offer some recommendations for the future. Okay, so as the introduction, in the world of rare earth elements, we have a set of 17 elements, including 15 lanthanides and yttrium and scandium. So these are the rare earth elements that we find in the periodic table. Then these rare earth elements are often categorized into two subcategories as light rare earth elements and heavy rare earth elements. So lanthanides from lanthanum to europium. Yes, it is really difficult to pronounce these metal names. They are considered as the light rare earth elements, and rest of the lanthanides as well as yttrium are considered as the heavy rare earth elements. So however, in this category, we don't find scandium because it does not occur in the same deposits as the other rare earth elements. And I should mention that compared to light rare earth elements, these heavy rare earth elements are scarce as well as they are very expensive. So do you know that most of these rare earth elements are actually not as rare as their name suggests? For example, if you go to a playground, collect some soil samples and analyze it, yes, you may find some rare earth elements. So it is not like gold and diamond. Okay. In fact, they are found in similar abundance in the earth crust as many other industrial metals like copper, nickel, chromium, and all that. So, for example, you can see the abundance of cerium is almost same as copper. So then, why are they called rare? Well, the term the rare is used because we do not find them in economically concentrated deposits like some other minerals. So instead, they are scattered across the globe in relatively low concentration. So like other minerals, the metals like copper and other industrial metals, we don't find these rare earth elements in very economically concentrated resources. There are over 250 minerals that contains these rare elements, no doubt, but among them, only few are commercially processed for the production. The main ones include basnasite, monazite, cenotyme, along with this locorite. However, an interesting type of rare deposit is known as iron absorption deposits, often found in southern China. In these deposits, rare ions are weakly adsorbed onto the surface of the clay minerals, and therefore they can be easily extracted through in situ leaching with using leaching agents like ammonium sulfate instead of strong acids. When it comes to the properties of these rare earth elements, they possess unique physical and chemical properties, making them essential for a wide range of high-tech applications. These properties include strong magnetism, high thermal stability, electric conductivity, and luster. Now, you can see in this figure, it showcases the various applications of these rare earth elements across different industries. With their versatility as well as indispensability in modern technology, are referred to as the vitamin of the modern industry. So now let's take a look at the reserves and mine production of these rare earth elements, and it is typically represented in terms of rare earth oxides. According to the USGS, the global rare earth mineral reserves are projected to reach around 130 million tons of rare earth oxides by 2022. Now, turning our attention to this figure 1, you can see the distribution of these rare earth mineral reserves in 2022. So, as usual, China leads the pack, holding the largest share at 33.8%. Then Vietnam accounts for 16.9%, making it the second largest shareholder. So let's examine the global mine production of these rare earth elements in recent years. According to the USGS in 2020, the production reached around 240,000 tons of rare earth oxides. Then this increased to 290,000 tons in 2021, and also for the rose to 300,000 tons in 2022. So now let's focus on this figure 2. You can see the distribution of global rare earth mine production in 2022. So China continues to maintain its position as the dominant producer, accounting for 70% of global production in 2022 compared to 57.9% in 2021. So normally in these mines, cutoff grade for rare oxide is around 1.5%, and it can range from 1 to 2.5%. So this is an interesting story because China continued to hold its monopoly in the rare earth industry, especially downstream processing, keeping an 85% share of processing capacity and manufacturing over 90% of permanent magnets in 2022. So with this context, across the globe, currently people starting this rare earth production here and there. Therefore, there are over 146 mine projects, as you see in this map. One notable deposit is that the Mount Bell deposit in Western Australia. So it is renowned as the richest rare deposit in the world. So you can see in this map the contribution of that deposit to this supply chain. So Lynas Rare Earths, it is an Australian listed company. it has been processing rare earth ores from Mount Well deposit at their concentrate plant. But due to some environmental issues, these concentrates are then shipped to the Lynas Advanced Material Plant in Malaysia. So it is the largest and single rare earth processing plant outside China. So now you can feel the grip that China has when it comes to rare earth elements. Here, if you are interested on these rare earth elements, this is one of our publications. So if you want to read more about what's happening in the rare earth industry, so this article would be a good resource, and it provides valuable insights into the industry's current state and its implication for the future. So now I'm moving into the rare earth permanent magnets from rare earth elements. Okay, so here you can see different types of permanent magnets. So before the advent of rare earth permanent magnets, these magnets are primarily made from materials like iron oxide, aluminium, nickel, and cobalt. So these materials had their strengths, but they couldn't match the performance of rare earth permanent magnets. Now, with the introduction of the rare earth permanent magnets, especially magnets like neodymium iron boron magnets, the game has changed. So these magnets boast highest magnetic properties among all permanent magnets, which revolutionizing the various industries as well as some applications. So in this figure, you can see the relative volume for the same magnetic power for these four types of permanent magnets. So for example, in early 1990s, we know the size of these speakers, but currently the size of the speaker is about earpods. Then I'm moving into the role of these rare permanent magnets in these green dreams, or let's say climate target. So when it comes to this figure 5, it is the forecast of neodymium iron boron magnet consumption up to 2032 by RF4 Resource Limited. So in this figure, you can see that other applications remain almost stable, but consumption forecast for wind turbines as well as electric vehicles rises each year. So in figure C, you can see the impact created by wind power and electric vehicles to the projection of these rare demand. So now you feel that they are not just magnets, they are the driving force behind our green revolution. So let's see the role of rare permanent magnets in wind turbine applications. Imagine driving of wind turbines in offshore wind farms. Behind the scenes, these magnets are integral to design these synchronous generators, making wind turbines more efficient, streamlined, and lighter, especially to use in offshore wind farms. So each offshore wind turbine requires a significant amount of neodymium and praseodymium per megawatt of power. So it showcased the crucial role of these permanent magnets in our transition to sustainable energy. By 2030, the European Union is expected to need 13,000 tons of neodymium and praseodymium solely for their wind turbines. So then the demand projected to soar even higher by 2050. So in this tale of innovation, rare permanent magnets emerge as the driving force behind our green dreams, powering our future wind energy. Then let's take a look at the role of rare permanent magnets in EV motor applications. So in the world of electric vehicles, these magnets play a crucial role powering their motors. A typical EV motor requires approximately 1.5 kilograms of neodymium, and well-known Toyota's Prius hybrid car. So it incorporates about 1 kilograms of neodymium into its motor. So with the global shift towards the electric vehicles to achieve this zero carbon emission challenge, the demand for EVs is skyrocketing. This exponential growth in EV adoption translates into staggering demand for these magnets, and it estimated to reach around 322,000 tons by 2032. So it's clear that rare earth permanent magnets are driving the future of transportation towards sustainability. In this figure 8, you can see the other applications of rare earth elements in EVs as well. So in this story of this rare earth permanent magnet, we find some challenges in global context, and there are some bottlenecks. For example, we have limited global supply to cater ever increasing demand. Therefore, there is a demand supply gap. So then in addition to that, we have some environmental concerns because when we process them, sometimes, for example, monoxide, there is a radioactive waste. And especially with these geopolitical concerns, we have market volatility that we need to address. And there are some performance issues, especially in different temperature ranges of these permanent magnets. So to address these bottlenecks and challenges, there are some current developments and some potential solutions. For example, diversification of the supply. So if we can generate at least rare earth concentrates all over the world in some places, then we can diversify the supply. And then we need to find some alternative magnet materials to replace some of these rare earth permanent magnets. And then with the available magnets, we have to improve their performance, especially working in different temperatures. So if you are interested on these rare earth permanent magnets, there is one of our publication. It provides valuable insights on the rare earth permanent magnets, especially on key industries like wind energy and transportation for shaping up the future renewable energy goals. Now let's see what we can find in Sri Lanka. So in the geological terrain of Sri Lanka, there are some potential primary resources like phosphate deposit, granitic pegmatites, and granitic rocks, and some hydrothermal veins. And there are some potential secondary rare earth resources as well. For example, mineral sands, especially in Pulmode, then clay deposit, some laterite deposits, and some gem-bearing sediments, also called gem mining waste, and some offshore resources as well. So in this map, you can see the our explored locations or the resources of these rare earth elements. So in this presentation, I will focus mainly on a phosphate deposit and gem mining waste. So for those who are eager to explore further about these rare earth resources in Sri Lanka, we published another review paper. So it compared the global rare earth element resources alongside the insights into the prospect of Sri Lankan rare earth resources. So I'm moving into the first case study. It is a phosphate deposit. So it is discovered in 1971 in the North Province of Sri Lanka. So normally it has two sections, northern deposit and southern deposit, as you see in this geological map. So in the northern deposit, we have 40 million tons of reserves, and in the southern deposit, we have 20 million tons of reserves, so altogether 60 million tons. So associated with the leached apatite bearing rock, so it forms a 50-meter thick phosphate-rich layer on top of carbonatite bedrock. So this deposit contains two main components. First component is apatite crystals, primary apatite crystals, and the second component is secondary phosphate matrix, as you see in this figure 11 clearly. So this intense weathering dissolves and recrystallizes these crystals, making it one of the world's richest phosphate deposits. Here, in figure 13, you can see the simplified flow sheet of the processing plant of this phosphate deposit. So since 1974, this deposit has been mined by Lanka Phosphate Limited. Most of the deposit is highly weathered, therefore it is easy to excavate using excavators, particularly in the southern deposit. Therefore, we rarely find this drilling and blasting. The excavated phosphate ore is generally processed to produce two fertilizers, that is high-grade phosphate with the content of 40% of P2O5, and then a phosphate, or so-called 28% of P2O5 in this ERP using the secondary matrix. In the southern deposit, primary apatite crystals are easily separated using grizzly and used for the production of HGRP. But in the northern deposit, these primary crystals are embedded, therefore it is harder to separate, so they are used for the production of low-grade DRP. So in the processing plant, they produce only one fertilizer at a time, especially to use in perennial crops like tea, rubber, and coconut. The issue is in the deposit is that the solubility. Since it is low solubility of phosphates, we cannot use them for the short-term crops. Now let's see the rare potential of this deposit. So this deposit contains a significant concentration of rare elements compared to the other phosphate deposits all around the world. For example, in this slide, you can see both apatite crystals as well as secondary phosphate matrix contain around 4,000 milligrams per kilogram of average total rare earth elements. So despite its relatively low rare grade compared to the other rare deposit in the world, still this deposit is enriched in critical and highly demanded rare elements such as neodymium and praseodymium, which are used for these for the production of these permanent magnets. So for those who are interested on understanding deeper into the rare potential of this deposit, this is another insight. So this paper includes the enrichment, mineralization, and economic significance of the rare elements in this deposit. So now let's see the extraction potential of rare elements in this phosphate deposit. We have carried out leaching experiments, and to select the best leaching agent. Here in this figure, you can see that, and nitric as well as sulfuric acid, they showed comparatively low leaching efficiency, especially when it comes to sulfuric. Normally, we use sulfuric acid for the production of some fertilizers such as single superphosphate. But the issue is when it in the rare context, when we use the sulfuric acid, it forms insoluble gypsum as a byproduct. So most of these rare elements present in the leachate, they are associated with this insoluble gypsum. Therefore, they are not freely available in the leachate, and we experience a low leaching efficiency as a result. Therefore, we have HCl and phosphoric acid as the suitable leaching agents. But we should not forget that the main component is phosphate in this deposit. Therefore, if we use HCl, then when we do the fertilizer production, chloride ion can be an issue. Therefore, we selected phosphoric acid as our leaching agent to extract rare earth elements from these primary apatite crystals at the phosphate deposit. So this is a general flow sheet. This is a proposed flow sheet for recovery of rare earth elements from primary apatite crystals. With our leaching optimizations, with the optimized conditions, we are able to leach out 91% of total rare earth elements from the apatite crystals. Then followed the solvent extraction. So we use the triene-butyl phosphate as the solvent for this solvent extraction experiment, and we achieve 79% of total rare earth element extraction. Here the issue is that in Sri Lanka, we don't find very efficient solvent for rare earth extraction. And during our studies, we tried to purchase them from outside Sri Lanka, but unfortunately, we had to take some very critical permissions as they are flammable. So therefore, unfortunately, with all these economic prices and all that, for the experiment we have carried out so far, we are unable to use these efficient solvents studies. But then we followed the stripping experiments using sulfuric acid under these optimized conditions. So then we are able to strip 91% of total rare elements. So in this flow sheet, you can see that we are trying to produce rare oxides. So, but it would be a byproduct during production of phosphate fertilizer. So we proposed a liquid phosphate fertilizer. We extract the rare earth elements from the leachate. But yes, the byproduct would be rare earth oxide. But when it comes to the price, it is more valuable than the phosphate fertilizer currently. Now, with that iron absorption clay deposit in China, we had a hypothesis. In this figure 17, you can see the phosphate deposit, and you can find Jayaganga, or so-called man-made water canal flowing across the deposit. And our hypothesis is that with the runoff, these particulate matter as well as dissolved substance can coming into this water canal, also called Jayaganga, and it can brings all these rare bearing materials to the downstream lake and accumulate there in the sediments. So there can be a potential rare potential in downstream lake sediments. So downstream lake is Kirlogama Lake, as you see in this figure. And to assess this potential, we collected some surface sediments as well as pore sediments from all these 3 lakes nearby the deposit. And then we assess the rare potential. Here, you can see the spatial distribution in figure 90 of the rare elements in surface sediments. So then in figure 20, you can see the vertical distribution. So it's on the vertical, core samples that we have taken. And then we assess the rare potential, and we found that downstream lake sediments has higher rare potential. That means it should be the contribution of the phosphate deposit. And like in the iron absorption clay deposit in China, so we carried out some leaching experiments using leaching agents like ammonium sulfate, and then we tried to optimize the entire process. So if anyone is interested on reading the rare potential of these lake sediments, we have 2 publications. First one, assess the rare potential in these lake sediments, and second one, the leaching results and what are the future of these lake sediments and how we should extract these rare elements from there. Then I'm moving into the second case study. It is gem mining waste. So we all know that Sri Lanka is one of the wealthiest countries in gems. Therefore, gem mining is extensively carried out in many areas of the country. Therefore, the gem mining industry produce a large amount of waste, but mainly they are used only for the backfilling. So there can be some hidden pressures there in this waste stream. So we have selected Kaluganga River as our as for our initial studies. So it is the second largest river basin in Sri Lanka. So it originates from the central hills, and due to the tropical climate, extensive weathering occurs, leading to a high sediment yield. So as a result, this weathering process, gem-bearing sediments are transported by the Kaluganga River, and deposited in alluvial layers, particularly in all river channels and floodplains. For our study, we selected gem pits along the Kaluganga River, where the gem layers are found in an all river channels, and we observe organic rich clay layer underneath that gem-bearing sediments. So we collected gem-bearing sediment samples, also called gem mining waste, from these gem mines, and we subjected them to primary sieving to remove the gravels, and then secondary sieving to remove mainly the silicate fraction, and as you see in this figure 22, and then we followed the density separation using shaking table. So here we have the heavy fraction we obtain after the separation, and we considered it as the concentrate, and we are interested on this concentrate to assess the rare potential. So we have carried out some analysis. Then from this XRD analysis, we identified some rare bearing minerals like monazite and xenotime in the concentrate, and parallelly we carried out some SEM analysis as well. Therefore, it confirmed the presence of light rare earth elements and yttria in gem mining waste, also called that concentrate. Okay, the presence of monazite justified the high concentration of light rare earth elements in these samples, while xenotime was identified as the primary mineral which takes all these heavy rare elements, especially the yttria. So then in our shaking table test, we found that 37% of material formed the concentrate, while the rest became the tailing. The concentrate had a total rare earth oxide grade of 3% with a recovery of 74%. So then that 3% means it's beyond the cutoff grade after this density separation. So notably, light rare earth elements show high recovery rates. So this indicates that the potential of the concentrates as the secondary source for rare earth elements, particularly for light rare earth elements. So for this context, we have published one research article. So here you can see that, and if you want to read more, you can refer to this research paper. Then interestingly, as I told you before, we observed the organic rich clay layer underneath the sediment bearing alluvial layer along the Kalu River. So therefore, initial analysis revealed that this clay layer holds a certain amount of rare earth elements, particularly these heavy rare earth elements, including yttria. So given their high market value, we decided to expand our research to assess the extraction potential of these rare earth elements in this clay layer. Then we carried out some leaching experiments with the use of sulfuric acid under these optimum conditions. We are able to leach out more rare earth elements there, and also it's all about 94% of rare earth elements were leached. Then, in addition to that, we have carried out some kinetic modeling and analysis, as well as some thermodynamic analysis for these experiments, and here are the results that you see in this figure. Now, with that, I'm moving into the conclusion of my presentation. First of all, this phosphate deposit holds uh, promising potential for these light rare earth elements, especially elements like neodymium and praseodymium. And then the next thing is that, yes, we are producing these phosphate fertilizers there. When we apply these fertilizers into the agricultural field, that means we are wasting our rare potential in that deposit. So if uh, we need to think about that as well. So when we compare the rare earth oxide grades of our phosphate deposit with some other phosphate deposit in the world, it shows some sub-economic potential. Therefore, we have to uh, develop a novel process to extract these rare earth elements before we are too late. So then when it comes to the gem mining waste, it is better to estimate the entire process and how much we generate the gem mining waste, and then we can estimate the entire potential of this gem mining uh, chain. And then this holistic approach not only benefits the country economically, but also it reduces the environmental footprint of gem mining waste. During our studies, we experienced certain amount of challenges. First challenge is that unavailability of more efficient rare extractants and ion exchange resins in Sri Lanka. Sometimes we cannot purchase them due to some rules and regulations here, and therefore what we can do is we can go up to the maximum level of leaching, but thereafter we need to find different ways to extract rare earth elements from the pregnant solution. Then another challenge that I was experienced throughout my research studies is that limited awareness of the among these stakeholders. For example, these gem miners and gem mine owners, they do not know that there are some rare earth elements in their waste, or so-called, especially in so-called Nambu in gem mining. So it hinders the development of rare earth sector or the industry in Sri Lanka. So with that lack of awareness, it leads to insufficient fundings for these areas, and some investment to scale up these lab scale level findings to pilot scale as well as the industrial scale to grow potential of the sustainable rare earth industry in Sri Lanka. So then I have some recommendation for the and future perspectives, especially when it comes to Epala phosphate deposit. It does not have this radioactive component like we find in monosite at Pulmode deposit, because these rare earth elements are isomorphically substitute in the apatite crystal. So with these low radioactive issues, if we can produce these rare earth concentrates at least while producing these phosphate fertilizers, then it would be a really it would be economically benefits to the country. And to do so, we need some collaborations with multidisciplinary research and developments with the combinations of government bodies, research institute, as well as the private sector. Then only we can develop, because we just I have carried out these experiments in lab scale. So to scale up, we will find some technological difficulties as well. With all that, I have some achievements as they introduced as engineer Ravindra introduced me at the beginning. So if you want to know more details about these rare earth elements and Sri Lankan potential, so you can contact me. And then these are the references that I use. So with that, as I conclude today's presentation, I'd like to extend my heartfelt gratitude to the Institution of Engineers Sri Lanka, especially to the ESL Western Australian chapter for inviting me to share my research finding and experience with you all. And special thanks goes to Engineer Ravindra Salgadu for his valuable support. I also like to acknowledge my research team at University of Morato at the Department of Earth Resources. Together, we are taking strides toward the unlocking the potential of rare earth elements in Sri Lanka, contributing to a greener, more sustainable future. And finally, thank you all for your time and attention. And it would be a great honor to deliver this presentation in front of this very enthusiastic audience. Thank you very much. If you have any questions, you can ask.
Thank you, Nimila. It's really informative presentation and whole lot of publications came out of your research studies. Fantastic. Congratulations on your future career. Yeah, we're very proud of you. Yeah, it is interesting presentation. And the audience, now it is your time to ask questions from Dr. Nimila. Nimila, I have one question. So when you talk about the Kaluganga and the rare earth elements deposition in Kaluganga, I know that because Kalutara is where I came from. So I know that there are several stations, the water taking out for drinking purposes.
Yeah.
Do you think that there's some side effects of having heavy metals contamination in the drinking water because of these rare earth elements?
Actually, with our results, I could say that no, because these rare earth elements are mainly deposited in all the river channels and other floodplains. So normally, yes, there is a potential that if these rare earth elements, especially minerals like monazite, contaminates the groundwater or the drinking water sources, but mainly we don't find that effect because we have to upgrade this waste after taking from that area. Then during that upgrade, only we enrich the metals like thorium. But when they present there, their content is very low. So rare earth elements we normally discuss in ppm level. Therefore, the effect is really low. During my studies, I don't find any water contamination from these rare earth resources, but there could be some different sources in that area as well.
Oh, okay. Yeah. Thank you. Yeah. We have one.
I think we have one question in the chat box.
Yes. So how are the rare earth magnets different from other magnets? Why they are better? Yeah.
Okay. So good question. First of all, so in these rare earth elements, their electron configuration is different compared to the other metals that we use to produce other types of magnets. Therefore, they can produce very strong magnetism. As I told you, with a small quantity of especially neodymium iron boron magnets, it can generate stronger magnetic power. Therefore, currently we choose rare earth permanent magnets over the other permanent magnets. So it is mainly because of their electron configuration as they produce strong magnetic power.
Yeah, thanks. Any other questions?
And there is another question in the chat box. Are the rare earth elements concentrated in Nambua? In that case, collecting raw materials? would be. Yeah. So normally we find these heavy rare metal, heavy minerals in the Nambu. So if we can collect only the Nambu, then it would be a potential source for rare earth elements, especially along the Kalu River.
So are we exporting rare earth elements at the moment?
No,
Or yes?
currently only in Pulmude deposit, these Lanka mineral sands, they produce the crude monoxide. So they may export in the form of monoxide, but not as the rare oxides as we do the processing.
Mhm. It means that we have a long way to go to meet
Yeah,
the
yeah,
environmental footprint to put on the earth. Yeah.
yeah. That's the issue.
Yeah.
So as I told you, there are some challenges because the
Challenges. Yeah.
lack
Mm.
of awareness,
Yes.
unavailability of these high-tech processes, especially these solvents and ion exchange resins.
Do
At
you
least
have
what
any
we
plan? Yeah. Do you have any plan for future to raise
yes,
awareness? Oh,
yes,
yeah.
yes. Currently, we are planning to, uh, I mean, develop a process to produce at least rare earth oxides from these sources and try to scale up it to the industrial scale as well. And in addition, nowadays we are looking at the e-waste as well. For example, these permanent magnets that are coming from these mobile phones, laptops, and all that, then recycling them to produce rare earth elements.
Okay. Yeah. That's great. Do we have any other questions? That's a thank you note.
Yeah, thank you very much.
Yeah. All right. If we don't have any more questions from the audience, I would like to give a big thank you to Dr. Nimila and coming through, come and deliver this presentation. And it's a very insightful and very informative, and it's a new knowledge. I think it's a new knowledge adapt to our audience today. And also thank you to Ravindra for organizing this and coordinating with Nimila. And thank you for the audience for participating and spending your time at Thursday afternoon. Hope the presentation will give you a new knowledge added up to you. And finally, thank you very much for everyone. Thank you.